Today we'll perform a lab on percentage differential relay using MATLAB Simulink. We have to simulate the differential relay, and that has to be incorporated in a simple power system where AC voltage source is supplying power to a load through a transformer, and we have to protect the transformer from any internal fault. Now let us consider one transformer or any equipment in a system. So we have to protect this equipment from any internal fault. So if we consider this equipment as a transformer, then we have to protect this transformer from any internal fault. What does it mean? Suppose here we have drawn a transformer which is supplying power to a load, and suppose the load current is 20 ampere in 200 volt side. So obviously at 400 volt side the current will be 10 ampere. So that 10 multiplied by 400, that is 4000, will be equal to the 200 multiplied by 20, 4000. So power at both ends will be same. If we consider that there is no loss in the transformer. So in per unit, we can say the same per unit current is flowing in both the sides. Now, if fault occurs just outside this CT, suppose I have drawn here, suppose the current fault has been occurred here, and due to that fault, this current will be now higher. It may be say 200 ampere. So instead of 20 ampere, this might be 200 ampere, and accordingly here the current will be 100 ampere, and when it is reduced in the secondary side and when it is reduced in secondary side, suppose here the CT ratio is say 10 by 1, and here the CT ratio is 20 by 1. Okay, so when 20 ampere flowing here, the 1 ampere current will be flowing in the secondary side of the second CT, and when 10 ampere current will be flowing in the primary side, then CT secondary side of the CT1 will be 1. So both the current basically same. Even if the fault occurs outside this arrangement, suppose the fault occurs here, and as I've said, if the current becomes higher than 20 ampere, suppose 200 ampere. So if the current here is 200 ampere, the current here will also be increased, and that will be 100 ampere. So it is 200, then it is 100. Again, the current in the secondary will be same. So when it is 200 ampere current due to fault is flowing, then the current here will be 10 ampere. here, if 100 ampere flows in the primary side of this transformer, main transformer, then here also the current in the secondary will be 10. In the both case it is 10. Now this difference, see the connection diagram, this 10 ampere is coming from this side and this 10 ampere current is coming from this side, and it is fed to the operating coil of this relay. It's simply overcurrent relay that we have already studied. Now, as the both currents are same, then the ampere turn here will be 0. So no torque will be produced on this disc, and the disc will not rotate. Even when there is fault outside the disc. So the fault current may be very high, but still the disc will not rotate. So our aim is to protect this transformer for any fault inside the transformer, not outside the transformer. That's why we don't want this relay to be operated during any fault outside this transformer. Okay. Now, if the fault occurs here, then obviously the current in this side and the current in this side will be different. So if the fault current is say 20 ampere, suppose if I say fault current 20 ampere, and the current which is flowing here 10 and it is 20. So after the fault occurs, the current here will be 20, but here it is 20 plus 10, 30. Okay, so 10 ampere for load current, 20 ampere for load current here, and the fault current will not flow in the secondary side, only in the primary side the fault will flow, fault current will flow. So now there will be difference between these two currents. So obviously the difference of the current will produce the torque. So that differential current, that's why it is known as the differential relay. So that differential current will cause the torque, and the disc will rotate. As a result, this cross arm containing the contact points will move in this direction, and ultimately these two contacts will be connected, so the trip coil will be energized, and that will send signal to the corresponding circuit breaker. So that is the main operation, and it is a simple differential relay. Now there is a problem of using this type of relay. Now we have considered that this ratio is 10 by 1 and this ratio is 20 by 1. But you know, if though these two CTs are identical in nature, still there may be some error uh, in them. So there may be some error, very minor error. But if the fault occurs outside and if the fault is very high, then the current here and the current here will be much, this current will be different for any higher value of the fault outside this zone. Okay, and that is due to the small difference in the CT ratios. Very small difference. Suppose one is, say, I can say 10 by, suppose it is say not one, say 0.5 9, 9, 1. And another here it is say 20 by say just 1. So there is a slight difference, and that difference will be more if the fault current is more. Okay, so if the fault current is more, though it is external fault, still there is a difference of current in these two cities. So that differential current will produce torque in the disk, and disk will rotate, and ultimately this uh, trip circuit will be energized. So it is not our desirable condition. So we don't want this relay to be operated when the fault occurs outside this thing, for any external fault. It should operate for any internal fault. But here, due to the error, very small error in the CT ratios, there may be unwanted relay operation due to the external fault. Now, to avoid this, what we can do? We can modify the circuit or connection, or we can modify the relay itself. Now, how? So here is an arrangement. See, now again the current here and current here, the current here and the current here for normal operation basically same, and that may not same, but in the secondary side these two currents are same, we can say. But for any external fault, uh, there may be some difference. But for that difference, this relay should not operate. That is our main intention. And another thing, if the fault occurs within this zone, that is known as the internal fault, then the relay should operate. Okay, so it can segregate these two types of faults properly. Okay, it can take decision. Okay, so this should be too much sensitive about the place of the faults. Now, in addition to the operating coil, there should be restraining coil. So uh, what is done? So this differential current will cause the disc to rotate in this direction, and this restraining coil, and you can see the current in the restraining coil 1 is this current, and the current in the restraining coil 2 is this current. Okay, and restraining coil total number has been divided into two parts, NR by 2, NR by 2. And this restraining coil is so placed that, or so designed, or so connected that these two current will produce torque in this direction. And the disc will rotate if this torque, or we can say the Ni, which is producing this torque, is greater than the Ni, which is producing this. Now, the Ni number ampere turn which is producing this torque, operating torque, is this N0. If I say the number of turn is N0 and the differential current is K I1 minus I2 is the trans ratio of the CT, and that should be greater than NR by 2 I1 plus I2, and K is the ratio. Okay, so we can say this I1 minus I2, the differential current, is equal to NR by N0 I1 plus I2 by 2. One is known as the differential current and another is known as the through current, or see, it is I1 plus I2 divided by 2, means just like average. So that average current is also called through current. So this differential current, and now this is through current. Now if I divide this differential current divided by through current, so it will give a ratio. So if I take this differential current I1 minus I2, this differential current divided by through current I1 plus I1 plus I2 by 2. So the differential current by the average current or through current, that should be greater than this ratio NR by N O. O for operating coil, R for restraining coil. Now if I take NR as 30 and NO as 100, what does it mean? So that is basically 30%. So if the differential current becomes 30% of the average current, then it will operate. So if it is more than 30, then it will operate. Okay, then we can make NR 20 and this as before 100, then it is 20%. We can make it 40, number of turn in the restraining coil 40 more, and the number of turn in the operating coil 100, then 40%. So we can set any of this, that is in our hand. Okay, so there is a provision in the relay where this percentage setting can be varied. Okay, so how much current, how much differential current will be allowed, that that depends on this percentage setting. So that modification, after that modification, this relay is not no longer safe as a simple relay. It's a differential, percentage differential relay, percentage bias differential relay. These are all known as the bias. 30% biasing, 20% biasing, 40% biasing. In normal practical differential relay, there are three such settings: 20%, 30%, and 40%. Now, how will we simulate this relay? Now we'll simulate that relay in MATLAB Simulink. Here's a complete circuit diagram. We have to protect this transformer from any internal fault. So first you see the main circuit, which is comprising of this AC voltage source, then a transformer, then transformer, and this is the load.